Yes, so good morning from me as well. To start off the program, we start with Professor Dietrich Borchardt. He is head of the research unit Water Resources and Environment at the Helmholtz Center for Environmental Research, UFZ. And he also holds a chair of aquatic ecosystem analysis and management at the Dresden University of Technology. And he will present on the GlobeWQ project and the Global Water Quality Challenge.
So now it should work. Hello, everybody. I hope you can hear me loud and clearly. So it's my pleasure to give the introductory talk to the GlobeWQ project and the Global Water Challenge. And I'd like to give and to revisit all the process and the context of the project GlobeWQ that is part of the discussion today. So now the scrolling works. So clearly GlobeWQ is placed in a wider context. And one of this context is that on the one hand side, we all know that water is a limited and scarce resource worldwide, which is shown at scale in this left sketch. By the way, the big drop is all water on Earth, and the tiny drop placed over Georgia is the fresh water which is available. And clearly, there is this SDG process and agenda that we all know about. And clearly that there is this SDG 6, which there was a debate about the content when this goals were developed, and I very much appreciated from my perspective that the scope was taken broader, and that it was not just about water quantity, drinking water, and sanitation, which was a discussion at the beginning. But SDG 6 extended then to include aquatic ecosystems and ambient water quality, which I think was really important. And therefore, a good ambient water quality was and is a challenge. And clearly, it's not only a goal on its own, but it's relevant in at least at a minimum 3 priority context, I would say, and this is the connection to the health and integrity of aquatic ecosystems, and therefore the aquatic ecosystem services. It's definitely relevant in the context of human health and food security, and therefore this was taken as a target and an objective of the project. The GlobeW project itself was, after some efforts, funded in the context of the Global Resource Water Initiative, which was funded by the German Federal Ministry of Education and Research. The funding program was active between 2017 and 20. So GlobeWQ was a little bit, started in this period, but extended over 2020. And the basic idea of that funding program was that these measures should address global analysis and local solutions, and emphasizing an integrative perspective on sustainable water management. And therefore, it also then has some logical connections with the GlobeWQ project. The project of the GlobeWQ was then also, as I said, a step in a wider agenda, which basically started early in 2016 with a publication of a snapshot report and an analytical brief by UN Water. Joe Alcamo was also involved, Martina was involved, and some others, including also Hartwig Kremer at UNEP. A basic outcome, which was very important, was that this triggered the UNEP resolution on water quality assessment management in 2017, and therefore it was important that this UNEP resolution called for an effort with regard to the assessment of water quality. Then the process started also designing this GlobeWQ project with a global coverage, but also at the same time with use cases. And then it continued with a number of events, and three major ones with regard to the outcome were workshops regarding the baseline assessment, the modeling in Delft, then remote sensing in Leipzig, and then also with COVID, we had to switch to virtual meetings. And but we could continue to work on the in situ data challenge and the integration. So at the end, there were products and that we are discussing about, and one definitely is the GlobeWQ report, which was recently launched. An important effort. I have some problems with the yeah, now here it is. With switching the slides, it's a little bit delayed, sorry. So what were the starting points and which were innovations which came from the GlobeWQ project? Definitely one starting point was a limited global coverage of the in situ data. Of course, it's improved over the last years with all the efforts to advance GEMSTAT, both in the data coverage, but also in the performance of the data flows. The approach of GlobeWQ was then that basically the intention was the science-based improvement of water quality information, but not only on in situ data, but with this so-called triangulation approach, also employ a modeling, global water quantity and water quality models, and also the innovations which come from remote sensing, and with all the advantages, but also with the limitations of each of these three sources. But the idea was then to synthesize these as much as possible with regard to scenarios, which includes a baseline assessment, the status quo, but also future projections. So this was an important, I think, methodological innovation which came with GlobeWQ. And then with this process, also the World Water Quality Alliance, this initiative, also supported by UNEP, was started and became active and is active. And there's an interplay with the global the GlobeWQ project. As I said, it was the agenda, SDG agenda, it was the UNEA resolution, and there were the case studies. And then with the World Water Quality Alliance, there was an effort to improve our knowledge, advance our knowledge with regard to water quantity, quality in relation to human health, food production, and ecosystems. And more and more also in the question, which is definitely also important for the future, what is the role of the socioeconomic dynamics and the diverse impacts of climate change we see. The effort then was that this project was, of course, not only, it was coordinated by UFZ, as Christian said, but University of Bochum were involved. There were also KMUs, EOMAP, especially terrestrials. We will see contributions today. But importantly, also we were linked with implementation agencies, including UNEP, Federal Environmental Agency, Germany, and the European Agency as well. But also the UNESCO efforts, especially with regard also to GEMSTAT. Here are the outcomes. I think it's a significant outcome with all the publications which were already launched. But I'm really I think really that now the final GlobeWQ report is yeah, visible but also substantial outcome, and for me a kind of benchmark. And by intention, the title was taken as Quality Known, because it shows what we know, and this could also be, I hope, for a bit of discussion about this in the course of the webinar today, because we all know that there were other publications that stated the opposite statement about the water quality unknown. So very much looking forward to this discussion. This is my introduction. Thank you very much for your attention.
Thank you very much, Dietrich Borchardt, for this nice introduction and setting the scene. Please remember, mute yourselves if you're not speaking, and please post any questions in the chat. I will collect them, and the questions will then be answered in the Q&A session at the end. So next up is Professor Martina Flörke. She is the head of the Institute of Engineering, Hydrology and Water Resources Management at the Ruhr University of Bochum, and she will present insights from global water quality models, current state and future scenarios. Thank you.
Yeah, thank you, Hans. Dear ladies and gentlemen and colleagues in the online room, it's a pleasure for me to talk about the insights from global water quality models, so the current state of water quality, but also on future scenarios. The results that I showed today, they are a team effort. And here I would like to thank my colleagues, Jaime Rivera, Ellen Künast, and also Hans Dürr. So on the text on this slide shows the motivation for our work. As already introduced by Dietrich, first, the SDG 6.3 by 2030, improve water quality by reducing pollution and so on. So this has been the first and, let's say, the big motivation to conduct this project. However, the snapshot report has also been a motivation because the snapshot report published in 2016 did not cover the global extent. So we extended our modeling to the global scale. And third, the UN Water Analytical Brief. We want to address the analytical brief because there was the request to look into the future. And this is something that we did in GlobeWQ. In the baseline report from the World Water Quality Alliance, published in 2021, this report portrayed the impacts of water quality on human and ecosystem health, as well as on food security, and was a milestone in using our baseline results. And last but not least, the recent IPCC report does not yet say much about water quality, and there we need to bring in more of our efforts. Whoops. That was too fast. Okay, good. Why global scale? I mean, most of the reasons were already given in the motivation. However, water quality degradation is a global problem, and it is further affected by global changes, and therefore demands for looking at these problems from the global scale. With the global scale, we can also support the SDG research. We can take a look into the interlinkages between different SDGs. And by using modeling water quality results at the global scale, we can provide information to data-sparse regions. We can identify hotspot regions of severe water quality status, hopefully better understand the future changes, and finally quantify indicators showing the interlinkages between the SDGs. This runs too fast. Sorry for this. On the global scale, or for the global scale, large-scale water quality models do already exist, and the number of these models is growing. So although similar in structure and also in methods being used or implemented in the models, these models simulate different water quality parameters, as you can see in this orange box. For example, biological oxygen demand, nutrients, fecal coliform bacteria, or microplastics. The models do calculate these in form of loads and or in-stream concentrations, but on different scales and in terms of temporal and spatial dynamics and extent. In GlobeWQ, we further developed and applied the world-crawl model, which is part of the Water Gap 3 framework. So a little bit more about the world-crawl model, but other models have a similar structure and work in a similar way. First, pollution loadings are calculated on a grid cell level, and then, depending on the source, partly entering rivers and streams. The simulation of the pollutant concentration is then a result of the dilution capacity of a river, meaning the river discharge and flow, and several in-stream processes such as decay as a function of water temperature in terms of BOD, or die-off bacteria related to solar radiation, sedimentation of bacteria like we did for the fecal coliforms, and also retention for the nutrients.
Thank you.
So as an example, we take a look at the development of fecal coliform loadings between the year 1990 and 2015. The diagram on the right-hand side shows the coliform forming unit per year for different point and diffuse sources. As point sources, we regard domestic sewage, so everything that comes into the river from treatment plants, for example, or from manufacturing industries, and diffuse sources like the manure that is washed off from the fields, or the domestic non-sewered sources. It becomes visible from this figure that fecal coliform loadings have grown over time, particularly from the sewage system, which is in the orange colors. This indicates an increase in population connected to sewage systems, but also that the treatment requires improvement. So improvement has not taken place as it should have been. So this map now shows the results of the median monthly fecal coliform concentrations for the year 2015. 2015 is the year of adopting the Agenda 2030 for Sustainable Development, and therefore is of importance for the monitoring and the reporting of future changes and improvements. So taking a look at the legend, the green river stretches, they have concentrations below 200 coliform forming units per 100 milliliters, orange between 200 and 1000, and the red colors display rivers where a concentration of 1000 CFU per 100 milliliters was exceeded. So the high fecal coliform concentrations, they become visible on all continents in the world, but especially in Asia and also in Europe. We identified these hotspot regions on densely populated areas with insufficient or even no existent wastewater infrastructure, but also in regions where the rivers have low dilution capacity. The river stretches turned out to be in red. So picking some countries out of the map and counting the number of people who are potentially at risk to getting in contact with fecal coliform polluted water is shown by this diagram. So we used the same classification as explained on the map before. And we can clearly see from these diagrams that in these few countries alone, millions of people were potentially affected to get in contact with fecal coliform polluted waters exceeding 1000 CFU per 100 milliliters. So for example, in China, it's about 50 million people being at risk in the year 2015. But what about the future? The diagram on the left shows the development of future FC loadings per source and according to the shared socioeconomic pathway 2, so SSP2. Until the end of the 21st century. Although the loadings from domestic non-sewered sources increase until the 2050s, the overall reduction in loading is a result of a decrease in fecal coliform from domestic sewered sources. So improvement takes place, but it takes a while before we see the improvement becoming visible in the FC loadings. So it's an indication for the improvement in sanitation and the progress being made. But an acceleration of the progress is visible to the end of the century. The sewer infrastructure and treatment levels, they are key drivers to determine the fecal coliform loadings. And scenario data, according to the SSPs, these were provided by Peter van Puyenbroek, so you can get an impression on how he did it. And you can see that the development in infrastructure and treatment levels depends on the economic development of a country. However, many other inputs and assumptions are required to model scenarios. And in 2 workshops that were funded by the World Water Quality Alliance, the community of water quality modelers developed 3 fast-track water quality scenarios where I showed just the results for one of these scenarios. Based on the FC loadings and the hydrological input that was driven by climate forcing from 4 different GCMs, we simulated the monthly fecal coliform concentrations, and the median for the year 2030 is shown in this map. So I assume you are now seeking for the changes compared to the map for the year 2015, and it's hardly to see. And indeed, the two maps, they look rather similar, but there are some differences. And these differences are visible in Asia, they are visible in Europe, and also in the US. And this is due to the fact that we have an improvement in sanitation that definitely reduces fecal coliform concentrations. In Africa, on the other side, the sanitation improves in almost all countries, but later in the century. So beyond the year 2030, mainly starting in 2050 or even later. So there were no big changes. Even in some regions, the colors get from yellow, from orange to red. And the pace of sanitation improvement is too slow to become visible in Latin America. Using the indicator SDG 6.3.2 and being applied for the fecal coliforms in 2030, this leads to the maps shown here. So the indicator presents the proportion of rivers and streams within a basin with good ambient water quality. So coliform forming units per 100 milliliters below 200. And the good news is there are big parts in the world which are colored in blue and in green, so indicating that more than 60% of the river basins have a good water quality related to fecal coliforms. But on the other side, there are many rivers and basins colored in red and in orange too, indicating that the SDG target will not be met in 2030. So coming to my conclusions. So for FC concentrations, hotspots are in densely populated areas, particularly where wastewater treatment is limited or even non-existent. Wastewater production still increases, but the reduction of FC loadings by improved wastewater treatment likely reduces the pressure on human health. And this is visible in Asia, in the US, and in Europe in 2030. In Africa, for example, a higher number of population is expected to be at risk of getting in contact with FCs in rivers in 2030 due to population growth and almost no sanitation improvements until 2030. In Latin America, FC hotspots are still present in 2030 due to the slow pace in improving treatment levels. Semi-arid regions seem to be more threatened due to higher pollution levels as a result of lower dilution capacity. And last but not least, there is still a strong need for regularly monitored, up-to-date, and readily available data in order to validate the model. Major contributions have been reached, but challenges still exist. So all the model results that we prepared will be made available for further analysis on the GlobeWQ platform. The water quality baseline, we provided data and got insights into the impacts. The scenario analysis for the world water quality assessment provided the fast track scenarios that we used to prepare our results and looking into the future. Last but not least, now the new efforts have been made in bringing in water quality as part of the global water sector and also the regional water sector in the EasyMap and ProCLIAS initiatives. And still, as a challenge, multimodal and multi-substances assessments are hard to address, and this is something that we will proceed in the future. Thank you for your attention and looking forward for our Q&A phase.
Great. Thank you very much, Martina Flörke. And it's good to see there are some first questions in the chat already for the Q&A later. So please continue to post your questions there. And then next we have Masuma Batul and Rohini Kumar from the Department of Computational Hydrosystems, also at Helmholtz Center for Environmental Research, UFZ. And they will present on nitrogen pollution legacies in Europe. Thank you.
Yes, hello everyone. I hope you can hear me clear and loud. Yes, I'm Masuma Batul and I'm doing my PhD at Helmholtz Institute for Environmental Research, supervised by Rohini Kumar. Today, I will be talking about long-term trajectory of nitrogen surplus across Europe. What I will present today, I will start my presentation with introducing to the problem that we are dealing with. The second part of my talk would be about long-term trajectories of nitrogen surplus across Europe that we worked, and we published the research paper in Nature Scientific Data last year. The last part of my talk would be about assessment of different typologies of nitrogen surplus across Europe. Starting with the aim of our research work within the framework of GlobeWQ project. So we are working for nutrient modeling at regional scale. In our case, nutrient is nitrogen and region is Europe. We want to understand the long-term trajectory of different components of nitrogen surplus across Europe, and we want to study the long-term impact of nitrogen legacy stores on nitrate level over European landscapes. As we know that worldwide surface water suffer from high concentration of nitrogen compounds that has multiple impacts on environment. For example, damaging the water quality, loss of biodiversity, and eutrophication. It is very important to realize that N level not only depend on current nitrogen N input to the system, but also on the past nitrogen N input that has accumulated over time in soil and groundwater, so-called legacy stores. Therefore, information on long-term annual nitrogen input and different components of nitrogen surplus is essential to better understand these legacy stores and to inform future land and water management strategies. Moving towards the long-term trajectory of nitrogen surplus across Europe. But first, I would start what nitrogen surplus is. Nitrogen surplus is the difference between nitrogen inputs from different sources. For example, nitrogen input from mineral fertilizer, from animal manure, from atmospheric deposition, and from nitrogen fixation, and nitrogen output through end removal from harvested crop and animal grazing. So the difference or the leftover after nitrogen output from nitrogen input is nitrogen surplus. There are existing data set for nitrogen surplus across Europe, but it has limitations. For example, it is either available for limited time period. As you can see here, this is nitrogen surplus given by European Environmental Agency in 2005, or the data set is available at a coarser spatial resolution. What we aim is to construct and analyze the long-term trajectories of different components of nitrogen surplus across Europe. So we constructed the individual component of nitrogen surplus at a gridded higher spatial resolution of 5 arc-minute, which is approximately 10 kilometers at the equator from 1850 till 2019. How we did that? We collected data set from different sources that were available at different levels. For example, global cropland gridded data set from HIDA or different component data set available at country level from FAOSTAT. Since these data sets were collected from different sources and were available at different time period and different spatial resolution, we first harmonized them to have a consistent data set across Europe at annual time steps. We process this data set, and one example of that processing is to downscale country-level mineral fertilizer information using gridded cropland and pasture area to estimate gridded cropland and pasture distribution of fertilizer to cropland and pasture areas. We assess these data set, and here is just an example of how we reconstructed mineral fertilizer data set. I would not go into detail of these flowchart, but if you're interested, I would be happy to talk afterward, or you can read our nitrogen surplus paper. As I mentioned, that the collected data set that we used to construct nitrogen surplus were very scattered because it was collected from multiple sources and different time period. It brings uncertainty to our nitrogen surplus estimates. To account for these uncertainties resulting from different data sources and from different methodological choices, we constructed these uncertainties in major component of nitrogen surplus, which are highlighted in red characters here. And ultimately, we have 16 data set for nitrogen surplus at grid level across Europe during 1850 till 2019. Here are the plots presenting spatio-temporal variability of nitrogen surplus across Europe at grid level. These plots are presenting the mean of these 16 nitrogen surplus estimate given in the unit of kilogram per hectare of the grid cell area per year. Regarding the spatial variability, overall, we observe that the Northern European countries has lower estimate of nitrogen surplus. There are higher estimate of nitrogen surplus in Western European countries, presenting by this yellow color, and there is moderate values of nitrogen surplus in Southern Europe. Regarding temporal variability, we observe that up to 1900, majority of the grid cells do not exceed N surplus greater than 20 kilogram per hectare. But around 1990, approximately 70% of the grid cell have the values around 80 or more than 80 kilogram per hectare of the grid cell areas. Afterward, there is a subsequent decrease in nitrogen surplus estimate, which is very apparent in countries, for example, in Germany, in many of the East European states. As we constructed the data set at grid level, it offers flexibility to aggregate it any higher spatial resolution, for example, at NUTS level. Here are the plots presenting nitrogen surplus at the NUTS 1 level, NUTS 2 level, NUTS 3 level. It is important because aggregating nitrogen surplus at country level could hide substantial differences at sub-country levels, as we can see here. Our dataset also allow us to aggregate nitrogen surplus estimate at river basin level. It is critical because river basins are relevant spatial unit for water quality modeling for land and water use management. These plots are presenting uncertainty in our nitrogen surplus estimates. On y-axis, we have agriculture and surplus given in kilogram per hectare of agriculture area per year. These red lines are presenting nitrogen surplus, and this gray ribbon is presenting minimum and maximum of 16 nitrogen surplus estimates. Overall, we observed from 1850 till roughly 1990, the width or the magnitude of the gray ribbon is more or less similar to the mean estimates predicting less uncertainty, but there are more uncertainties afterward in countries such as Belgium and the Netherlands. To assess the consistency of our data set, we compare them with the previous existing data set because we lack the direct observations. And overall, we found that our estimates at the continental and different European countries level capture reasonable well with existing studies. Moving toward the last part of my talk of today, which is about assessment of different typologies of nitrogen surplus across Europe. Since the European landscape differ among each other due to differences, many factors such as socioeconomic and land use and management practices. And therefore, nitrogen pollution is not equally distributed in Europe. To assess that, we apply a multidimensional clustering algorithm to our nitrogen surplus dataset using self-organizing maps. I would not go into detail of SOMs, but just to give some basic ideas. So it used some inputs that feed into the algorithm and as an output, we got cluster that share similar characteristics. In our case, we feed the algorithm with the constructed nitrogen surplus components and land use. And as an output, we got 4 dominant nitrogen surplus cluster across Europe. Here on the left side, there are 4 identified clusters, and on the right side, there are n fluxes among those clusters. The first cluster, manure, which is a man cluster, which is presented by dark orange color, covers mainly the West European countries, and it is mainly dominated by animal manure, as can be seen here by the dark green bar plot, which shows the contribution of nitrogen input from animal manure. The third cluster that mainly covers the Central European countries has high dominancy from nitrogen input from mineral fertilizer that can be shown here by light green bar plots. The third cluster, which is more cluster in this purple color, is mainly covering the East European countries and Mediterranean countries, has the moderate dominancy from both fertilizer and manure. And the last cluster is NAT cluster, which is mainly covering the natural Northern European landscapes, and it has dominancy of an input from either atmospheric deposition and nitrogen fixation. It is important to note that the contribution of nitrogen input among those typologies differ among each other, and also the magnitude of nitrogen surplus vary in these clusters. Although the temporal pattern of nitrogen surplus was similar in all typologies, for example, there was an increasing pattern of nitrogen surplus in early development phase, and then there was a decrease in nitrogen surplus in other phase, which is sustainable intensification phase, but the magnitude of the N surplus typologies differ among each other. It highlights the need for regional specific target to reduce agricultural nitrogen pollution in Europe. I will conclude my presentation with some takeaways. The nitrogen surplus dataset that I presented provide basis for analysis of past and present estimate of nitrogen surplus. The dataset is publicly available. And as I showed before, the landscape in Europe is not equally burdened by nitrogen pollution. We identify different clusters in Europe, and currently we are working to assess whether a uniform strategy to reduce nitrogen surplus across Europe apply everywhere. For example, recently European Green Deal introduced some strategies to reduce mineral fertilizer, and Europe for having nitrogen surplus, for example, and we want to assess the feasibility of these strategies across European landscapes. Last but not least, as in my introduction, I mentioned a point that current nitrogen input does not only depend what we put currently, but what has been accumulated over time from the past. And nitrogen surplus, or the excess of nitrogen that is in the soil, goes ultimately anywhere or somewhere in the environment. And one is the leach down of that nitrogen surplus in groundwater. So high nitrate levels in groundwater often stem from these historical nitrogen surplus, which accumulate over time and continues to impact water quality. And we need to remember our action today have a lasting impact on tomorrow. Thank you.
Thank you very much, Masuma and Rohini. Again, if you have questions for Masuma or Rohini, please ask them in the chat. I will collect the questions and they can be asked in the Q&A session at the end. So then next up, we have case studies. They will be presented by Karin Schenk, who is with EOMAP, a small remote sensing company in southern Germany, and Christian Schmidt, who you met, who he did the introduction, and he is with the Department of Hydrogeology at the Helmholtz Center for Environmental Research, UFZ, and they will present on case studies the implementation of the triangulation approach that you already heard about from Dietrich Borchardt. Thank you.
Thank you, Hans. I take the freedom to start, and then Karin will join in the second part of the presentation. Yeah, so the GlobeWQ case studies, they are distributed across rivers and lakes, and they also cover like 3 continents. And these are the regional examples of implementing the prototype of the platform, but also the implementation of the triangulation approach. Before we get to the idea of the triangulation, we have seen it several times already. I would have a brief view on the technical side of the GlobeWQ platform. So basically, we have very different data. We have remote sensing data. We have model outputs from different models, and we have in situ data that come, in our case, from the GEMSTAT database, but also other database connections would be possible. And for one case, we also have included an online sensor data from the so-called Undine network in central Germany. So these are connected to a geo server and a database via programming interfaces or by a simple data fetcher. And the front end, that's the Shogun WebGIS. That's part of our partner Terrestris. So they are developing it, and this is basically what you see when you go to the different applications. The whole system is modular, and so we have different portals for the different cases, and the entire system is based on open standards, so it's interoperable with other systems easily, and data could also be accessed via or data could also be delivered, data products via web services. But back to the process of getting to the platform. So some of the case studies that are driven by our own motivation because there was a urgent water quality issue, like last year in Central Europe at the Oder River, where there was a large fish die-off. We will hear later about it. But many of the use cases or case studies, they're driven by a bottom-up process, or by a co-design through workshops with stakeholders. So we try to find out, okay, what is the need and how could we deliver a tailored solution? And what was also important during the process, so we had a startup where we collected the basic ideas for the design, and then there was also continuous feedback. Feedback was on the one hand more formally, like in follow-up workshops, but then I'm very grateful to it. I'm not sure if someone is in the audience, like also like informal feedback where I received an email, yeah, feature A, feature B is not working, or how to handle this and that. So that was very important to improve the usability of the platform. Okay, but have a look at the triangulation in more detail. So the idea is to combine different data sources, and all these different data types, they have pros and cons. Like in situ data, of course, it has a high acceptance. It has very different parameters. Whatever you can measure can be provided. It's ground truth for other methods, but the spatial and temporal coverage is limited. Remote sensing, on the other hand, it provides near real-time information. It has a very high spatial temporal coverage, but you're limited to water quality parameters that can be optically detected, like chlorophyll or turbidity. And of course, the models, they are the only tools that actually can make predictions for the future, or you can do scenario analysis with them. That's only possible with the modeling side. And the idea of GlobeWQ is to combine all 3. And I would very briefly go through a few case studies that we have implemented. So first one is the Elbe. That's a river basin in Central Europe, and our partner to design the platform was the so-called FGG. So it's a union of the the German federal states that are part of the basin, and they help to implement the EU's Water Framework Directive. As we have heard in the last talk, in Central Europe, there's a long-term nutrient pollution. That's also an issue at the Elbe, and there's a risk of algal blooms. And there is near real-time water quality data, but the stations are very sparse and spatially. So we needed information in between. And the idea is to use satellite data to provide information on remote, on chlorophyll and other parameters, and to basically to close the gap between those monitoring stations. And currently the GlobeWQ platform is operational. So with every overpass of the satellite, given there are no clouds, the data that's available is updated. A second case study I would like to highlight here is the Lake Sevan. The Lake Sevan is in Armenia. It's very relevant for the country of Armenia for freshwater and food supply. And here, our project is very grateful to other projects, for example, the Sevamod projects, because they have already established partner networks there, so we could benefit from them. The photo on the lower right, that's in the environmental ministry of Armenia. And the lake faces various pressures on water quantity, but also on water quality. So, and there's currently data collected and also information systems built up. So it was very important for us to be interoperable, with the other developments, so that we can connect, that we could connect to the other systems. And what we did, because water quantity is an issue, we used the hydrological model MHM to quantify the inflows in the lake, and we also used the WorldCore model to quantify the phosphorus loadings to the lake. And remote sensing is used to provide water quality information for the lake surface. Last but not least, it's Lake Victoria. This is where we basically started through the use case process of the WWQA. So also here, we had the support of already operating projects to get in contact with the stakeholders. And Lake Victoria, you all know, has a high significance for the economy, particularly the fisheries sector for Kenya, Tanzania, and Uganda. But it's also under pressure from various sides, so which includes nutrient inputs, wastewater inputs. And because of the nutrient pollution, there's also a risk for algal blooms, which in turn is a risk for fish population and also for human health. And additional, because it's a multinational lake, basically, there's also a lack of data sharing policies and also partially capacities. We will hear in the next talk about Lake Victoria a bit more. And so also to overcome the data gaps, we use remote sensing to provide also operational data on chlorophyll concentrations, basically for the whole lake. So also this is updated on the platform with every overpass. We have established a interface to the GEMSTAT database. So basically you can access the data that's available at the GEMS water data platform. And also here, WorldQual is used to quantify the phosphorus inputs to the lake. So you can basically connect the state of the water quality in the lake, with the hotspots of inputs. And also because there was a wish from the stakeholders, there's an option to upload data. So basically a XYZ table, and to the platform, so you can visualize your data points in conjunction with all the other data. And but there's no need to really share the data with someone. So whenever you refresh the browser, the visualization will be gone. And then I would like to hand over to my colleague Karin to introduce the Oder case.
Yeah, thank you very much, Christian. Right now, I don't, you have to give me some permission. Yeah.
You get control immediately.
Yeah,
yes.
Thank you very much. So I will talk a little bit about the Oder catastrophe happening last year. So there was a massive fish kill, which was mainly caused by algae bloom of a brackish algae, but I will come to this later on. And so we try to, reconstruct this catastrophe by approaching the triangulation approach using satellite data, modeling data, and also in situ data, and try to reconstruct the space-time trajectory of these algae blooms and the fish kill. So this is a very nice summarizing image provided by Christian, where you see along the river how the concentrations of chlorophyll changed over the time on the x-axis and how the fish kills accumulated until end of or mid-August 2022. So let's see if it's work. Yeah, so I will dive deeper a bit into the different factors and early warning indicators, which helps us to overcome these kind of catastrophes with an early warning system by using this triangulation approach. And we have this kind of online dashboard where we have this early warning system installed. So the first one are the water level and discharge, which influences the nutrient concentrations in the river systems. Here we see from satellites, so we used here Sentinel-2 and Sentinel-3, so that's the Copernicus missions, and also the commercial very high resolution data of Planet to derive water level in the river of Otra. And we see that we have a very low level in June to August 2022. So that was the first factor which can be seen. What we also can have a look at modeled and in situ measured solar radiation or sunshine duration in this case. Here we use the ERA 5 data, and we see that we have in end of July and also early August very high values of sunshine duration, which is nice for us, but for the whole ecosystem, it causes some problem. What we also see, and that's especially a benefit from the satellite data, high resolution algae concentrations also from contributing rivers. So this is the Otra River in Opole, but we also see also from the side arms how the chlorophyll concentrations in this case can intrude into the river system. We also see here on the lower bar a high value of chlorophyll towards end of July and early August. Another point we can have in situ data, but they are often sparsely distributed. We have one, for example, in Frankfurt Oder in Germany. Here we have also the peak mid of August. But of course, here the access to the data is often limited, which is not the case for modeling or Earth observation data. Another important factor which was here also introduced was the release of saline waters from mining reservoirs like here Selani Most. So we see an animation of Planet Labs imagery, and also we can process this with satellite imagery and see really what is the water area. You see here in the red arrows times where there was some kind of change in the water area of the reservoir, probably to the release of the waters. So we see here in beginning of July already a release, but also mid or towards end of July and also in August again. So what we have done is try to combine different factors here from Earth observation, modeling, and in situ to have a combined risk factor, which we can access in this dashboard. Here we used, for example, this water level / sunshine duration risk factor. And we could see here in this display that we have already on the 13th of July, an early warning towards upstream of the Odra River. And if you go a little bit further in time, so on the end of July, we see that this has moved a little bit towards the midstream. And also we see a mid of August, let's say the answer from the system with high chlorophyll A values towards the Oder at Frankfurt station. Yeah, so to sum up, the combination of the different data information, so from satellite data, from modeling, and also in situ, can help to install this kind of an early warning system and help also to support the decision on management activities like stopping the release of potential mining waters, for example, in the case of the Odra River. And so this is our approach here. And it was a little bit fast, but I'm happy to answer any questions later on in the Q&A session. So thank you.
Great. Thank you very much, Christian and Karin. And as you just heard, both of them will be happy to answer questions in the Q&A session later on the Earth observation and related questions. Please remember the platform was established by Terrestris, and I think we also have two members from Terrestris in the audience today, Hannes Blitzer and Uli Rothstein, and they will certainly be happy to answer questions on the technical background of the platform if you have any. Otherwise, we have the last talk in this webinar for today, Andrew Gemmell from the Umwoto Foundation and SLR Consulting. He is based in South Africa and is showing a very nice, looks like a wedding picture here, and he will talk about the Lake Victoria case from a user perspective. Thank you.
Thanks very much. All right, let me progress. So my name is Andrew Gemmell, as it says there. So I'll be presenting on the Africa use cases, specifically around Lake Victoria. The Africa use cases were in three areas: Cape Town, aquifers, the Lake Victoria Basin, and the Volta River Basin. So basically covering three different types of water resources: groundwater resources for Cape Town, a lake surface water resource, as well as a river basin resource. And the Lake Victoria and Volta River Basin are both transboundary. So really useful use cases. I'm going to be focusing on the Lake Victoria use case and specifically talking around the stakeholder engagement process. You know, as you know, we may develop all sorts of products and services, but unless there's take up by the stakeholders, then it kind of falls flat at times. So I'll talk about that as well as the lessons learned regarding that. I think I can progress to the next slide. There we go. So I won't go through too much detail on what the triangle approach was, because it has been covered. But basically what we were doing was piloting a bridge from data to solutions. And the solutions is what was the importance of this. And the solutions has really been what has been the cause of the success of this project. And this project has been a success. So the aim was to define the demand for water quality services and link the water quality hotspots to solutions, and importantly to investment opportunities as well. It needed to be a bottom-up approach. It was no use providing a product to in-country stakeholders without the stakeholders actually having a need for it. So it was driven very much from engagement with the stakeholders. What do you want, and how can we produce something that you actually are needing? Why did we choose Africa, or why were the Africa use cases there? Well, Dietrich showed a very useful image of the spread of information across the world, and Africa just has a lack of information. And that information can be resolved by using this triangulation method, by using satellite imagery to resolve a spatial as well as a temporal limitation in data, modeling to forecast into the future, in situ data to validate both of the previous two types, which is really important. But in situ data is what is lacking, and the in situ data needs to be provided by in-country stakeholders. So what was needed was quite a detailed stakeholder engagement process, and that was through the Africa Great Lakes African Center for Aquatic Research and Education. So that's AGLAK. You can see it at the top of the screen there. And they have advisory groups. They've got advisory groups for every one of the 7 larger Africa Great Lakes. And so what they do is they meet monthly. I'm part of the advisory group for Lake Victoria. I continue to meet monthly. And we talk about the ways forward in terms of what might be needed, research, gaps, things like that. Importantly, through the great work that AGLAK has done over the last years, is that those groups each have very diverse representation. As an example, for Lake Victoria, it includes intergovernmental organizations. You can see some of them there, the Lake Victoria Basin Commission and the Lake Victoria Fisheries Organization, governmental fisheries organizations in Kenya, Uganda, and Tanzania, Kimfri, Tafiri, and Nafiri. Then there's also academic institutions, both local and abroad, and then international governmental, international organizations like the IASD and the WWF. So because of that comprehensive grouping, there's very robust discussions on what's needed, what are the problems, how can we take this forward. And when we start talking about products and services, that engagement forum is absolutely critical to say, hey, we're thinking about offering this. Are you interested? What can we develop? How can we develop it further? And there has been a lot of interest in the triangulation concept, especially around GlobeWQ. Oopsie, I've lost some. There we go. GlobeWQ. That's what it looks like. So if I jump to the next slide, catch up with myself. The stakeholder goal engagement started in 2019. It continues to date every month. The outcome of this was identification of a tool needed. So the stakeholders that I mentioned earlier identified the need to identify potential water quality hotspots related to coastal eutrophication. So that was really useful because we had already got to that point of understanding what the needs were, and then we could take that forward in terms of a Lake Victoria specific platform or portal on GlobeWQ. And those discussions around GlobeWQ continue. I will be presenting this at the World Water Quality Alliance meeting in Nairobi coming week, and I will actually be having workshops with the stakeholders on 2 of the night. There will be 2-hour each engagements to talk about how can these things develop, how can we develop it towards funding. And so on the screen there's GlobeWQ. I won't go through it in too much detail, but broadly what the for Lake Victoria, what the stakeholders are interested in is the triangulation of that data to fill in the gaps of what's needed. And so what we're wanting to do is taking it forward, and largely what we want to do is through really finding out the underlying trends and hotspots, and we want to use that to identify where funding is needed, and that's what's really important. Obviously, the Royal University Bochum, IOMAP, UFZ, who we've had speakers by, are very important in this process. Triangulate the data, and you get this really useful platform that can be used to house the in-situ data from GEMSTAT, the satellite imagery from IOMAP, the modeling from the Royal University Bochum, as well as Helmholtz Center. And that easily accessible format is what's really been of interest to the stakeholders. Often satellite imagery or modeling sounds like a foreign concept. When it's actually on a portal, it's far easier used. But what is obviously lacking is in-situ data. You cannot have satellite imagery or model data without in-situ data to validate that. So we are taking this forward in a quite a structured way. In terms of the workshops, we are having workshops this coming week. It'll be about 4 hours of workshops, as I mentioned. As preparation for that, we wanted to canvass all of the Great Lake advisory groups, of which there's 7 advisory groups, to find out what their primary concerns and needs were. This was an update to previous work done. We got responses from all of the lakes, you can see there. Broadly, they're interested in what were the primary institutions, mostly government research organizations and private research organizations. So organizations like the fisheries organizations, Kimfree, Nafiri, Tafiri, which are the riparian fisheries research institutes, as well as universities. They primarily collect the data. What are the parameters most interested in? Clearly, eutrophication. At all of the lakes, eutrophication was seen as a major concern linked to that temperature, which is tied into that. So that was seen as a major interest in the lakes. Why is in-situ data not shared more often to forums like GEMSTAT, which is the Global Water Quality Database? And it comes down to trust, it comes down to funding, it comes down to protocols, it comes down to trainings, and all of that leads to a lack of data being shared. So those are items we want to specifically tackle. What might please some of those on this call is, what is the reliance on what data types? I expected it to be largely in-situ data, but it's pretty much an even spread between citizen measurements, scientific measurements out on the water or in the lab, automatic measurements like buoys set out with automatic measurements, Earth observation, modeled results, as well as citizen science. So broadly, there's a reliance on equally each of those, which is great to see to take forward, especially in this kind of triangulation approach, because automatic measurements in situ are lumped as one, as well as citizen science, to be honest. So the next slides are quite full of data. Those are the funding, the challenges that were there. These are the last two slides, so bear with me. The challenges were around funding. So there was a concern around funding, a lack of shared database options, a lack of data compatibility, especially cross borders, a lack of consolidated protocols and policies related to data sharing. Who has data? Who needs to share it? Trust was a big concept. Develop trust within organizations, between countries, and to break a north-south divide. There was a concept that came through quite clearly of a north-south divide, where the global north takes data from the global south and reaps the benefits of that data. So there needs to be mutual benefits, and training and capacity were additional items. How do we actually address that? Those are the solutions that are there. Funding is an issue. We know that. So what we're looking at doing is finding long-term sustainable funding as opposed to single projects, as well as agreements. Some of the data cannot be shared. The UN cannot take data at a cost. It needs to be shared voluntarily. The governments are actually quite happy to do that as long as there's a memorandum of understanding. So that needs to be put in place. Shared database options. Countries, individuals, research institutions all use their own databases. They store the data, they don't share it. So things like GemStat, GlobeWQ become really, really useful. Obviously, there's a concern around sharing of data, that it might be stolen. But GemStat has open, limited, restricted data use provisions. And so you can more easily share the data without a concern of data being taken. Specifically, GemStat, you retain the ownership of the data that doesn't get taken. Standardized protocols and policies for better sharing between countries, between institutions, and that includes standardized data types. Different countries might use different units, and so that's quite important to understand. Mutual benefit has been a very, very, very big identifier of trust. Is saying, how can we share data without somebody stealing the data, using it without citing the data? How can the benefit of me sharing the data come back to benefit me as opposed to benefiting some other organizations, institutes? And the last one of that was training and capacity development. We could talk about satellite imagery, we could talk about modeling, but unless there's capacity development in country for stakeholders, they won't take up those options because it's a foreign concept done by foreign organizations. So if there's more training and development, that's really important. How to take this forward? Last slide. If it pops up, there we go. Is the way forward on this is to refine and expand on the challenges and opportunities. So how can we get more data shared to GemStat? Once it's in GemStat, it gets pulled into GlobeWQ. How do we conclude which water quality platforms meet the user's needs? It might be GlobeWQ, it might be something else, but we cannot foist something onto the users without their input. The good news is GlobeWQ has been really well received by the stakeholders. So there's a lot of potential to take that forward. We want to then get individuals to share the data to that shared repository, to GemStat, so that it gets pulled into GlobeWQ. And then we want to expand this methodology. Why focus on Lake Victoria? Why not expand to the other Great Lakes using the existing methodology? The other Great Lakes have already said, yes, we would love this type of portal on GlobeWQ for our lakes. Obviously, it needs funding. So that's why I will be really focused on making sure that we identify what funding needs there are and funding opportunities to take this forward. But we are really excited to take this stakeholder engagement forward to link water quality hotspots to solutions and, as I said, importantly, to investment. So thank you, and let's open up to questions.
All right, thanks very much, Andrew, for this presentation. So this concludes the presentations, and this means we can move to the Q&A session. Please continue to post your questions in the chat. I will look into the chat and collect questions there, ask them for the presenters. And actually, the very first question we have in the chat is actually directed to Dietrich Borchardt, but it's also a nice link to the last presentation from Andrew we had, because it is about how you see future water quality information and the status in the next 20 years in terms of improvement and challenges? So the question goes to Dietrich Borchardt and is from Safe Joma with UFZ in Germany.
Yeah, thank you, Hans, and thank you very much, Safe, for this question. First of all, I really appreciate that you were asking about future water quality information, which, of course, like we saw in the various presentation, is something different when it comes to data. So, how do I see future water information systems? I think, as it said, as I termed it, I see really the future that we will hopefully see science-based water information systems and analysis platforms, because clearly the data and the environmental information that we get from the various sources, like we tried in GlobeWQ, need to be turned into useful information, both when it comes to and definitely with regard to different aspects. The first one is different time horizons. I think also the examples of our project clearly show that there's a need to understand the past and to work on and to understand the trajectories of the development. I refer to the two presentations given by Martina, and also to the nitrogen legacies we saw as good examples on this. Then definitely they need to be they have to cover today. So to overcome the delay that we saw in many efforts of the past, when it took and it takes or took and takes still years from a monitoring sample to be turned into a report, easily 5 years or more. So real time, near real time, and definitely up to date functionality is important, and also, of course, the future projections with regard to developments. But again, we saw very, very important examples today. Scalable is very important, definitely, with all the capacities we have now, with scaling in modeling, in extrapolation, with the remote sensing. The triangulation approach allows to cover the scales from nearly local, at a minimum regional, to catchment-wide, national, to whatever context we are heading for. So this is a functionality of the water information systems of the future. Very important is what Andrew just highlighted. It's the accessibility. It's the sharing, and it's the definitely the need to make these information readily available to a wide group of interested people, civil society, governmental organizations, NGOs, etc. And clearly, also these informations then have to make a link between water quality and underlying causes. So pressures and impacts perspective, which inform the understanding of a given water quality state, but also, of course, understanding the most effective entry points for interventions, and therefore definitely they should be useful and have to be made useful for management. And what I also see as a challenge of the future, I think they could also be and should also be more integrative when it comes to the water cycle, meaning they might include hydrometeorological information, definitely water quantity, most probably important compartments, cover more compartments, which includes soil moisture, definitely groundwater, and then the different surface water bodies that we have. So in this sense, have also the capability to have information on these interlinked compartments. So this is the future. I think the technical capacities will rapidly increase so that these technical problems in principle or challenges can be met. Of course, this needs to be done. And then it's clear that this needs also a long-term commitment. Andrew mentioned this as well, others as well, that we need an architecture that really operates these systems and makes these available. And this is also a challenge, of course, and a challenge for, or maybe a challenge definitely for institutions like U of Z as well. And here I can say that we will be and stay committed to the development of these systems, and therefore take the responsibility that we have as a national lab in water science. So short question, long answer. Hopefully I could address the points you made. Thank you.
Great, thank you very much, Dietrich Borchardt, for this answer. So I see already Martina has raised her hand, probably also in relation to that question from Safe. But this can already lead me to the question that is there for Martina, which is from Olaf Büttner, also from UFZ. And he has a very specific question on slide 22, where the whole of Italy is red, and he is asking what may be the reason there.
Yeah, before I answer the question of Olaf, I would like to get back to what Dietrich already mentioned. And I would really like to strengthen not just only the need for the monitoring of the water quality status, but also to getting more information and also data, in particular on the impact side. We do not know enough on the impacts of water quality on, for example, human health and ecosystem health. We get these connection by the presentation from Karin, so on the interplay of the different compartments, as Dietrich also mentioned too. So the hydrology situation in the water in combination with water quality, like the salinity intakes and water temperature, leading to algae bloom, and finally ending up in this dramatic fish kill. So this whole chain from the key drivers, pressures, so the whole dipsier approach that we can easily apply to this kind of a situation. I mean, we very often do not have this chance to get all the different parts of it, particularly the impacts. Coming back to the question from Olaf, I mean, honestly, this is a question that global modelers like, in terms of pointing on something and then getting an answer. So I took the time, because I have seen his question already in the chat, so I took the time and looked into the table, and the answer to this is clearly that for FC removal, most effective is this with tertiary treatment. And in Italy, there is a little bit more than 38% of all the treatment plants working in on the tertiary level. Compared to Germany, we have more than 90%. So this is the short answer to why we see Italy in red, and this is due to the treatment level. And this is what we get from the statistics. So.
All right. Thank you very much, Martina, both for the comment and also for the answer to Olaf's question. Then next, there is a question from Leif Wolf, who is with the Projektträger Karlsruhe, and he has a question for Masuma Batul about the nitrogen legacy and long-term effects that are known since, some time. Very interesting maps and work, and how is this information, how can this be made useful in environmental regulation decision making?
Yeah, I will take over the answer for Masuma on this question. Here is Rohini Kumar. I mean, like, because we work together on these particular issues. Well, what I can say is that once we know the areas that are persistently loaded with the nitrogen surplus, we can convert them as indicators and then give these indicators to the policymakers to understand which areas, despite a regulation put forward, is still not showing any changes in nitrogen surplus over recent years. And these kind of informations can be used by the policymakers to make us a judgment. But it's very interesting also to hear that one, that we know this problem, but despite we are putting up more and more and surplus in the region, which is also create more and more problems, right? So, and this N surplus is just a one part of the story, because the other part is that what part of that N surplus that ends up in a groundwater and in the surface water. And there we are doing a parallel study where we are developing our water quality models that tries to identify where the historical loads, or which is put into the system, will contribute to the long groundwater problems. And if we have those maps, we can definitely then try to push the policymakers to look forward why we are not getting any changes in the groundwater concentrations. So in that way, our map could be a useful way, or our data set can be useful way of translating this scientific information into some sort of indicators, which we are now also doing in our scientist domain to move the policy makers to think really forward the issues that we are facing, or we are not only facing now, but we will face forever if we don't start acting now. So this is what I would tell the short answer, or let's say a very generic answer to your question, Leif. Thanks.
All right, I see a thumbs up from Leif Wolf, so that's nice. Thank you, Rohini, for that answer. Well, next we had a question about the name of the platform, and actually Olaf provided in the chat the link to the platform, so www.globewq.info, and he also provided the link to the platform, so this question was already answered. Then we have actually a question to Karin and Christian about the ODRA early warning system and if this is available on the platform as well.
So I can briefly answer. So right now it's not included in the GlobeWQ platform. It's from EOMAP and an own EO app, let's say, dashboard designed. So if you have any questions, just contact me. But of course, we are trying to further improve and yeah, let's see how the projects after the lifetime of the project evolves and see how we can further integrate also this early warning system into the GlobeWQ platform.
All right, thanks very much, Karin. Then we have two kind of comments in the chat. The first one, I don't dare to try to pronounce the name in fear of mispronouncing. The first is about modeling and that this is bridging many gaps with regards to environmental management. And hopefully relevant stakeholders will take the necessary action to help protect the environment. And that also had a thumbs up. I don't know if anyone of the modeling people would like to say a few words or add that as a standalone comment.
Yeah, I mean, just a short comment. I mean, particularly this kind of projects is supporting this issue. So increasing more information, bringing more data also from the modeling side may help to support particularly those regions where we have almost no data. And I would say that from the, let's say from the global perspective and also the large scale perspective, our models have been used not just for water quality, but for water quantity since many years, even decades. And they are already, let's say, well established, not just only in science, but also from policy and also society side. And I believe that in, let's say, improving these models and bringing in additional information, this is particularly something where we can provide our support. And this has been done by the German Ministry of Research, and we could make it happen with this project.
All right, thank you, Martina. Then we do have, another comment from Andrew Gamel. He says one cannot manage or improve water resources without monitoring, and once a pollution problem is identified, then funding is opened up. So here we come back to funding, and solutions are found. And he emphasizes the importance of the triangulation method, that it is critical to filling in the gaps in water quality. So, Andrew, right? Thank you. You want to say anything else on that?
I mean, I think a practical example. I remember at one of the meetings, the World Bank was talking around, and they had funding available for a country, and the requirement to release that data was a water quality measurement of a river, of the main river in the country, to be available. There was not that data. They could not release the funding. All they needed was somebody to collect a water quality sample and send it to the laboratory. So without data, you can't find any solutions, and you can't release funding. And so this data and this triangulation method is so important to be able to identify these water quality hotspots, so that you don't necessarily need to delay project funding because of a lack of data. So I see a lot of potential for this.
Great, thank you. So then we have another comment also again from Leif Wolf, and he says that the ODRA case is very instructive and a great example for the use of online information. So disseminating this information might raise acceptance and interest. Yes, very certainly. And then maybe as a final concluding question, because I think it's a good question in terms of the future of the platform, is how do you intend to integrate other global water quality platforms or information into GlobeWQ? For example, Saudi Arabia has announced its support for the Global Water Organization.
I take it, Hans. Yeah, I'm not aware of the activities of Saudi Arabia, but I also would like to give a more generic answer. I think the solution is standardization, right? If you provide data in a standardized format, or if you provide even data as a web service that's standardized, other platforms can easily ingest this data. So what we try with GlobeWQ, so you can basically all the data that's available can be made available as a web service as well. So everyone can easily include it on another platform that uses the standard, and vice versa. So that would be the generic answer. Whatever one does in terms of information systems, use standards that can be taken up by other platforms, and the data can be recombined to a new data product based on the region, the topic. So I hope this was somewhat helpful, but not very specific.
Thank you, Christian. So I think with that, we can conclude the Q&A session. I'd like to thank you again for your interest and the good questions. And also again, thank you very much to all the presenters. And with that, Christian is going to conclude this webinar with some closing remarks, and a big thank you from my side as well.
Thank you, Hans. Yes, the only thing I want to tell is that the GlobeWQ project has ended, so there is a final report. It's available on the GlobeWQ homepage, so there are more details provided on everything that we have presented today very briefly. Also, the slides will be made available there, and I hope that the recording worked. Although the project has ended, the ideas of GlobeWQ and the World Water Quality Alliance, the triangulation, integrating data, making water quality information more timely, that will live on. As Andrew said, everything depends on funding. So we are actively trying to get involved in projects and funding. What I can say for now is that the website of GlobeWQ and the platform, it will be further maintained. So we will keep at least the status quo. We will ingest new data, for example, new modeling scenarios that will be coming. And yeah, so I hope that GlobeWQ will be around and for some time from now on. And yeah, I hope to stay in touch with you all and have a great weekend. And for some of you, see you next week in Nairobi. Bye-bye.
Thank you, Christian, for coordinating all the activities as well in the GlobeWQ project. Thank you.
Wollen wir noch? So. Wollen wir noch kurz ein Wrap-up machen für die, die noch da sind?
Gerne. Ich bleibe noch einen Moment drin, auf jeden Fall.
Ja.
Ich sehe noch 11 Teilnehmende im Moment.
Ja.
Sorry, ich muss mal ganz kurz ans Telefon.
Ja. Andrew, do you want to stay for a little wrap-up?
Ja, hallo.
Already gone.
We could also go to re-entering or somehow, I don't know.
Yeah, that's
because there are still some people there.
they're probably in hibernation. Yeah, I can close the meeting and we can meet under the same link right after. Okay, so meeting will be closed and who's interested can rejoin.
Yeah.
Okay, see you in a minute.